general relativity, it's been said that there was a time when only a dozen men understood it. At least one physicist, Richard Feynman, disagrees. In The Character of Physical Law, Feynman says, "I do not believe there ever was such a time. There might have been a time when only one man did, because he was the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people understood the theory of relativity in some way or other, certainly more than 12. On the other hand," says Feynman, "I think I can safely say that nobody understands quantum mechanics." The fact is that relativity, though difficult, can be grasped intuitively. Its conclusions and ideas can be drawn. Seeing the concept, no matter how strange, no matter how far removed from everyday experience, somehow makes it easier to accept. But how does one visualize a wave that behaves like a particle? Or a particle that behaves like a wave? Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. But if the universe refuses to limit itself to what man can imagine, how does one approach that comprehension? How, in short, does one approach quantum theory? Einstein was probably the first man to fully appreciate that human experience with the universe is extremely limited. More importantly, he made the intellectual leap to the realization that the very nature of time, space, or gravity might be vastly different from what it appears to be on the human scale. Consider the lesson of relativity. Everyday experience with the universe deals with velocities of tens or perhaps hundreds of miles per hour. Even 20th century technology can only attain speeds measured in thousands of miles per hour or several miles per second. But light travels about 25,000 times as fast. And at these velocities, the special theory of relativity must be taken into account. It is not that time and space behave differently at these velocities, but that there is a difference between the way they actually behave and the way we think they behave that only becomes noticeable at these velocities. In our everyday experience, those differences are so small they cannot even be measured. Consider gravity. The Newtonian equations and concepts work just fine near the surface of the Earth, or when calculating the orbits of most of the planets. But in the case of Mercury, the closest planet to the Sun, the effects of gravity begin to get stronger, and there is a slight but measurable difference between the Newtonian prediction of its orbit and the relativistic prediction. And in conditions where gravitational effects are stronger, the differences between the Newtonian and relativistic predictions become greater. In fact, even the special theory of relativity turns out to be strictly true only in the complete absence of gravity. Once again, it is not that time and space behave differently under different conditions, but that as the effects of gravity become stronger, the difference between the way they actually behave and the way we think they behave becomes noticeable. And once again, in everyday experience, the differences are so small that they cannot even be measured. Taken together, these different levels of understanding form a hierarchy of ideas. It may be strictly true that the interactions of space, time, and mass are only properly described by the general theory of relativity. But in conditions of high velocity and low gravity, we can safely ignore the general theory, act as if the special theory were exactly right, and still come up with the correct answer. Or, in conditions of low velocity and low gravity, we can act as if the common-sense Newtonian concepts of space and time are right, and still come up with the correct answer. In fact, each of these hierarchical levels can be, and usually is, discussed independently of the others. Each level is extremely useful within its own limits. And each level is essentially valid within its limits. Now, how can quantum theory insist that particles behave like waves when our experience insists that they don't? The answer is that the wave behavior of a marble, for instance, is hidden by the circumstances under which we experience it. It is a large clump of matter. As a result, its wave properties are so slight in comparison to its size that they cannot even be measured, though they can be calculated. It happens that all of our concepts about particles are based on experience with billiard balls, marbles, and the like. On that scale, we can treat the world as though particles and waves were two different things. The quantum mechanical aspects of matter only become noticeable when studying much smaller particles, electrons, for instance. Once again, we are dealing with a hierarchy of levels. Once again, it is not that matter behaves differently in the form of smaller and smaller particles, but that the smaller the particle, the more noticeable the difference between the way it behaves and the way we think it behaves. Quantum theory deals with a level which no one is even slightly familiar with. Mankind's day-to-day experience with the universe has nothing whatever to do with its behavior at the subatomic level. It turns out that our definitions of particles and waves are simply wrong. In our everyday world, we can continue to act as if they were right. But in our approach to understanding the universe on a small scale, we must be prepared to throw out the definitions, or at least to change them radically. In the end, the universe is like an Escher graphic, which, to be understood, must be viewed from several perspectives at the same time.